Welcome to section 16.5. In this section, we're going to be looking at a couple new concepts, a couple new types of calculations that we can perform involving vector fields. And we're going to see how we can use these to solve some problems. So to start us off here, if we have a vector field with components pi plus qj plus rk on R3, and the partial derivatives of all of these exist, then the curl of f is the vector field on R3 defined by the following. So this is the partial derivative of r with respect to y minus partial of q with respect to z I plus partial of p with respect to z minus partial of r with respect to x j plus partial of q with respect to x minus partial of p with respect to y k. Now, obviously, this is a formula that we don't want to have to memorize as is. We want to come up with a better way of remembering this and how to actually process this ourselves. So we're going to get a simpler notation. Consider the del operator, so that we saw back in a couple of the previous chapters involving the gradient, right? So when we operate the del operator on a scalar function, it produces the gradient. All right, so we have partial with respect to x, with respect to y, with respect to z. In and of themselves, these partial notations don't mean anything unless you apply them to something. So we're kind of just keeping them in here as placeholders. And then when we apply the gradient to a scalar function, we get partial with respect to x of f, and then partial with respect to y of f, partial with respect to z of f. And that gives us the gradient vector. Now, if we think of this del operator as a vector, we can take a cross product of that operator with our vector field. So we have the partial symbols here, and we have p, q, and r here. And instead of what we typically do is we would like multiply, right? So for the I component, we would block off row and column, and we would take, AD minus BC like that. We still want to do that, but instead of multiplying this times this, all we're really doing is applying this partial to that function. Okay, so we're going to have partial of r with respect to y minus partial of q with respect to z, and that's the I component, minus, block off j row and column, partial r with respect to x, minus partial of p with respect to z. So partial r respect to x minus partial p respect to z. And that's the j, plus partial q respect to x minus partial p respect to y. And that's the k. So if we compare what we had up above versus what we have now, notice that they're not 100% identical, but this one we have plus partial p respect to z minus partial r respect to x. This one we have a minus, and then these two have been kind of reversed here. So if we were to pull out a negative from both of these, right, out of both, that would become a plus. This one would become negative, and this one would become positive. And then we could just switch their order. So just a little bit of algebraic kind of sleight of hand here. But we do end up getting exactly the same thing, just in a slightly different form. So what this tells us is that if we want to compute the curl of the vector field, then all we need to do is take the del operator crossed with f. So del cross f will give us the curl of the vector field. So let's take a look at an example. So we have the vector field, find the curl of f. So curl of f. So again, that's del cross f. So we're going to have I, j, and k. Partial with respect to x, y, and z. And then the components of the vector field, those three. So xz, xyz, and negative y squared, like that. And now we compute the cross product normally, and we apply the partial derivatives. So we're going to get partial with respect to y of negative y squared minus partial with respect to z of xyz, that's I, minus, for j, we get partial with respect to x of negative y squared minus partial with respect to z of xz, and that's j, and then plus partial with respect to x of xyz minus partial with respect to y of xz, and that's the k component. We get a lot of simplifications in this one, so like that one, there's no x's, so that becomes 0. This one, there's no y, so it becomes 0. So we take these corresponding partials, so we're going to get negative 2y minus xy. So we can factor out like a negative y. So that's 2 plus x. That's the I component. This one, just negative, negative, so positive x. So xj plus, with respect to x, that's just yzk. So that new vector field that we just created, that would be the curl of the original vector field. One thing that the curl does for us that's going to be pretty helpful is this next theorem, top of the next page. If f is a function of three variables that has continuous second-order partial derivatives, then the curl of the gradient of f equals the zero vector. So the curl of a gradient vector field will be 0. And we can actually prove this. So I want to go ahead and kind of go through this process here. So we're going to get, so curl of the gradient vector field. So that's the del operator crossed with grad f or del f. So we're going to have I, j, and k. Partial respect to x, partial respect to y, partial respect to z. And then the components of the gradient vector field, those are just fx, fy, and fz. So if we take the partials here, so we're going to have partial with respect to y of fz minus partial with respect to z of fy, I, minus partial with respect to x of fz, minus partial with respect to z of fx, j, and then plus partial respect to x of fy minus partial respect to y of fx for k. And let me go ahead and write these all at the subscript notation just to kind of condense this a little bit. So this one is going to be fzy, this one minus fyz, I minus fzx minus fxz, j plus fyx minus fxy for k. And notice that in each of these cases here, the partials are the same variables, but not in the same order. However, as long as we know that we have continuous second-order partial derivatives, we can actually utilize a blast from the past, and that was Clairaut's theorem. Clairaut's theorem said that as long as you have continuous second-order partials, the order of the differentiation does not matter. So this would become, we could switch the order in any way we want. This would be fyz minus fyz I minus fxz minus fxz j plus fxy minus fxy k, which is 0i plus 0j plus 0k, which of course is the zero vector, which is what we were trying to prove. So we showed that the curl of a gradient vector field is 0, right? The zero vector. Now think about what we know about gradient vector fields. We know that if a vector field can be written as a gradient, right, a gradient vector field, then we call that vector field conservative, right? And we've done some talk about conservative vector fields for a little while now. Well, this result tells us that if f is conservative, then the curl of that vector field is 0. Okay, so before this, we could only test two-dimensional vector fields for conservatism, right? Because we had the partial q and partial p being equal to each other. And if they were, then it was conservative, given that the domain was appropriate. But that only worked for 2 dimensions. Now we have a 3-dimensional vector, okay, with x, y, and z. And we can see that if the vector field is conservative, then the curl would be 0. So, for example, this vector field, we've already worked with this one a little bit, so we already showed the curl of f. So this is just from the last page. We just found the curl here, so that's negative y times 2 plus x I plus xj plus yzk. So the curl of this gives us this formula in terms of x, y, and z. But if we're saying that the curl of f is the 0 vector, that doesn't mean that you can make it the 0 vector, right? Because you could plug in 0, 0, and 0 and make this the 0 vector. It needs to be 0 for all values of x, y, and z in order for this to be true. So since curl of f is not 0, this vector field F is not conservative. So we do get kind of proof to the contrary here, where if we know that the curl is not 0, that automatically tells us that the vector field is not conservative. Now, this is just like the problem we ran into in the other case, where this statement goes this way, right? If it's conservative, then the curl is 0. It does not necessarily go the other direction, saying if the curl is 0, then it's conservative, although we sure would like it to. It turns out that the converse is only true if F is defined everywhere. So if F is a vector field defined on all of R3, whose component functions have continuous partial derivatives, and the curl of F is 0, then F is a conservative vector field. Okay, so if we have a vector field that is defined everywhere on all of R3, and we find that the curl is 0, that means the vector field is conservative. And what does it mean to be conservative? It means that it can be written as a gradient field, okay? And that there is a potential function, right, whose gradient it is. So tying in a couple of the previous sections here. So let's take a look at an example, the top of the next page. So show that this vector field is conservative. So for part A here, so we're going to get curl of F. So I, J, and K. So we get partial with respect to X, partial with respect to Y, partial with respect to Z. And then our other components, I'm probably going to have to squeeze these in here. Y squared Z cubed, 2xyz cubed, and 3xy squared z squared. Sorry, that's kind of a tight fit there. So if we go component by component here, so for the I component, we go partial with respect to y of 3xy squared z squared, so we're going to get 6xyz squared, minus partial with respect to z of this one, so we bring down the 3, so we get 6xyz squared I, minus partial with respect to x of this, so that's 3y squared z squared, minus partial with respect to z, so bring down the 3, that's 3y squared z squared, j, plus partial with respect to x of this, that's 2yz cubed, yz cubed, minus, sorry, did I get these mixed up? Minus, no, that's right. Partial with respect to y, that's 2yz cubed. And that's the k component right there. Okay, now we should never expect these to turn into zeros. You should always go through the work and the process of showing that these become zeros, but these are the same thing, so that's 0i. These are the same, so that's 0j, and these are the same, so that's 0k. So we get out the 0 vector. So we're going to show that this is conservative. So the curl is 0, and then we check the domain. So just look at all of the input functions here and check for any domain restrictions, and there are none. Okay, these are all, like polynomial, like power function style terms. So we can say since the curl of f is 0, and the domain of F is R3. F is conservative. For part B, it's asking us to find the potential function. So now that we know that there is a function, little f, that has this as its gradient, we can use processes similar to the previous sections to actually find that potential function. But this one, because this is work from a previous section, I'm just going to leave this as an exercise for you all, but I will tell you what the final function is. You don't get a lot of surprises. It ends up just being kind of this one term here. So we get x, y squared, z cubed plus k, that constant. So if you're looking for extra practice finding potential functions, that's a great one to try out. So the curl is producing a new vector field for us. We know that if we have the curl of a vector field is 0, that the vector field must be a gradient field. The curl itself, though, when it's not just becoming 0, the curl itself, if you're thinking about what did this vector field tell us, well, I mean, it's kind of right there in the name. It's talking about the curl. So it tells us how much a vector field is rotating at any given point. Okay, so it talks about how much curling is happening at any given point on the vector field. So, and then of course, because we get a new vector field, you can then plug in any point you want to determine the value of the curl at that specific point. The next topic that we're going to discuss in this section is that of divergence. So if we have, again, a vector field with P, Q, and R components on R3, and all of its partials exist, then the divergence of F is the function of three variables defined by divergence of F is partial of P with respect to X plus partial of Q with respect to Y plus partial of R with respect to Z. So notice no ij or k in this. So this is a scalar field. And if you think about this in the context of, we just talked about taking cross products, right, when solving for the curl. This one, if you consider P, Q, and R to be kind of their own things, and these are the partials with respect to X, Y, and Z, we can frame this one very similarly using the del operator dotted with the vector field F. So just like we had the curl of the vector field is del cross F, the divergence of the vector field will be del dot F. So this is nice because the dot product is a nice kind of quick calculation for us here. So for this example, if we want to get the divergence of this vector field, we're going to take, so del operator dotted with F. So we're going to get partial with respect to X of XZ plus partial with respect to Y of XYZ plus partial with respect to Z of negative Y squared. This is Z plus XZ plus 0. And that's how we calculate the divergence. Okay, so the divergence, again, produces a scalar field, not a vector field. Okay, so these results they no longer have ijk. They are not components of a vector. They are their own scalar values, which we could then plug in a point and get out a number. Okay, so divergence is going to produce for us a number, whereas the curl produces a vector. What does divergence tell us? Well, if F represents the velocity of a fluid, for example, divergence measures the tendency of the fluid to diverge from the point xyz. So don't you always love it when people define things using the same word in its own definition? When we say diverge from the point, it's like the tendency of it to move away or to get away. How strongly does the fluid or the object want to get away from that point, okay, at any moment along the vector field, okay? So divergence gives us kind of the degree to which the current wants to move away from any given point. Okay, so that numerical value is telling us the strength. So if it has a really high value of divergence, it really, really wants to move away from that point. If it's a very low value of divergence, then it will want to stay, typically. We can also talk about relationships between the curl and divergence. So if we have a vector field F on R3 with P, Q, and R having continuous second order partials, then the divergence of the curl of F is equal to 0. So it turns out if you have the curl of a vector field, so you take the curl, you get a new vector field, and you take the divergence of that, you will get 0. We're not going to do like a full-fledged proof of this, but notice we need to have continuous second-order partials. If we were to take the divergence of the curl of F, remember that the curl represents del cross F, and the divergence represents del dotted with whatever that vector field is. So if we were to go about this process, the first thing to take note of is if you take the dot product of two vectors, notice that del cross F, the cross product of two vectors is orthogonal to both of the vectors that went into it, right? And this is more of a geometric idea. But again, if you have two vectors that are crossed together, the cross product is orthogonal to both. The dot product of orthogonal vectors is 0. So you're taking something dotted with something it's orthogonal to. So then it makes sense that it would become 0. The real kind of justification behind this is it uses Clairaut's theorem to cancel terms. So looking at it from the dot and cross product aspect gives us an idea of why this might work, but the actual proof involves Clairaut's theorem. So, but we're not going to go through that whole process. We're just going to try using this. So show that this vector field cannot be written as the curl of another vector field. Okay, so show that this vector field cannot be written as the curl of another vector field. So F is not equal to the curl of G, some unknown vector field. Okay. So for this one, if we let's go ahead and take the divergence of F. So we're going to get partial with respect to X of this. So that's 0 plus partial with respect to y of this, so that's 2xz cubed, plus partial with respect to z of this, that's 6xy squared z. Okay, again, no ijk. The divergence produces a scalar field, not a vector field. So what this tells us, just right out of the gate here, is that the divergence of F is non-zero. Right? And this one would be the number 0 because the divergence produces a scalar. So we know immediately that the divergence of this vector field is not 0, right? And again, that's not to say that you couldn't plug in numbers to make it 0, but it has to always be 0. So if it were true that f is equal to the curl of G, some unknown vector field, then the divergence of f would have to be equal to the divergence of the curl of G, but the divergence of the curl of G would have to be 0. All right, because that's what this theorem back up here told us. So again, if it was true that f is the curl of an unknown vector field G, then the divergence of f must be equal to 0. But we just showed that the divergence of f is not 0. Okay, and this provides us with a contradiction. So this cannot happen. So f cannot be written as a curl. The last thing that we're going to take a look at, just a quick note here before we get to a couple additional formulas. There is another differential operator that gets used, not so much in our class. We're not really going to encounter this more in here, but you could see it being used more in the future. So we just want to introduce it to you briefly. This is the Laplace operator. Occurs pretty frequently going forward. Again, not in this class, but in future application. And that it looks like the del operator, but it's squared. So this is del dotted with del is the notation sometimes used, or just partial squared respect to x squared plus partial squared respect to y squared plus partial squared respect to z squared. Basically, this Laplace operator acts as a second partial derivative with respect to x's, y's, and z's. So if we were going to evaluate second order partials for a lot of these things, we would use the Laplace operator. So the last thing to take a look at here, we just talked about Green's theorem in the last section. We have some different forms of Green's theorem that we can look at here. So it's kind of interesting to see how these interconnect. And we'll be looking a little more in the future as well at some of these connections. But remember what Green's theorem said, that if you take the positively oriented line integral over C, that is equal to, actually I can just scroll back really quick. That is equal to the double integral over d of partial q with respect to x minus partial p with respect to y dA. Notice this expression right here, partial q respect to x minus partial p respect to y. We have actually seen that pop up right back here in our first formula when we defined the curl. So it turns out if we just take the k component, the third component of the curl of the vector field, we can create Green's theorem. So if we look back down here, the line integral over C of f dot dr is equal to the double integral over d of the curl of f dotted with k. In other words, I and j both become 0. We only take the k component of the curl, and that's that formula. Okay. So we also have, so you can see, like, consider f to be p and q. The curl of f dotted with k is just that expression dotted with k. So we get out exactly what we were looking for. Okay, so there are definitely deeper connections here between all of these properties. The last one to look at, if we take the line integral of f dot n ds, so evaluating a line integral with respect to arc length, that's actually equal to the double integral over d of the divergence of f with respect to x and y. So it turns out if you have a normal vector n, so this is the unit normal vector, dotted with the vector field. This is one version of a line integral. We saw this back in like section 2, I think. But it turns out this relationship is equivalent to the Green's theorem relationship if you take the divergence of that vector field F. So we have seen now how to compute Green's theorem directly. We've seen how to find curl and divergence. We've seen how to use the curl in particular to show that a vector field is conservative. And now we see that there are even deeper connections between curl and divergence and things like Green's theorem. So we've still got lots of good stuff to look at coming up in the future sections of this chapter. And we're going to talk more about these line integrals, and we're also going to be getting into surface integrals as well in the coming sections. So I look forward to talking with you all very soon.